Thousands of galaxy clusters, each holding 1 trillion stars, appear to be streaming toward one small patch of sky, all in the same direction, at nearly the same speed. Nothing inside our universe should be pulling them. To understand why that's a problem, start with the oldest light in existence, the cosmic microwave background. It's the faint afterglow of the Big Bang, released when the universe was about 380,000 years old, and it fills the entire sky. That afterglow is almost perfectly even in every direction, but it's slightly hotter on one side of the sky and cooler on the other. That lopsidedness, called the dipole, tells us we're moving. The whole solar system is drifting at about 370 kilometers per second. Zoom out further, and the whole local group of galaxies is moving faster still, roughly 630 kilometers per second, pulled toward a dense region astronomers call the Great Attractor. Behind the Great Attractor sits something even bigger, the Shapley supercluster, the largest concentration of mass in our corner of the cosmos. Our galaxy is one small part of an enormous flow called Laniakea, all sliding toward that gravity. This is where standard cosmology makes a firm prediction. On small scales, galaxies get tugged around by nearby mass, but average over larger and larger volumes, and those tugs should cancel out. Zoom out far enough, and the net motion should fade towards zero. In 2008, a team led by Alexander Kashlinsky at NASA's Goddard Space Flight Center went looking for that fade out. What they reported instead set off a fight that still hasn't ended. Their tool was a subtle trick of physics called the kinematic Sunyaev-Zel'dovich effect. When background light passes through the hot gas inside a galaxy cluster and that cluster is moving, the light gets a tiny push in temperature, a fingerprint of the cluster's motion. That fingerprint is minuscule, far too weak to read on any single cluster. So Kashlinsky's team stacked the signal from hundreds of clusters together, combining X-ray catalogs of hot clusters with temperature maps from NASA's WMAP satellite. When they added it all up, across roughly 700 clusters, the clusters weren't moving randomly. They were moving together, a coherent bulk flow, all pointing at the same region of sky. The direction pointed toward the constellations Centaurus and Vela in the southern sky, not far, roughly, from the Great Attractor and Shapley regions we already knew about. But the speed was the shock. The team measured a flow of around 600 to 1,000 kilometers per second, and in later work, they claimed it climbed toward that upper range, and it didn't fade with distance. The flow appeared to hold steady out to more than 1 billion light-years, and in updated analyses, Kashlinsky pushed the claim to distances of 2 to 3 billion light-years. That is exactly what standard cosmology says should not happen. At those scales, the net motion is supposed to drop towards zero. A steady, directed current of galaxy clusters over 1 billion light-years has no cause inside the visible universe. Kashlinsky's team gave it a name, dark flow, a large-scale motion with no visible engine, mirroring the way dark matter and dark energy are named, for effects we see without knowing the cause. Whatever is pulling has to be enormous. The most striking proposal is that the clusters are being drawn by something outside our observable universe entirely, a vast concentration of matter beyond the edge of what we can ever see. The observable universe isn't the whole universe. It's just the part whose light has had time to reach us in 13.8 billion years. Everything beyond that horizon is real, but forever out of view. Dark flow, some argued, was that hidden mass making itself felt. One version goes deeper. During cosmic inflation, the instant of hyperfast expansion just after the Big Bang, regions now beyond our horizon were once close neighbors. A giant unevenness from that era could have given the whole region a gentle, permanent tilt in one direction. Push that idea to its limit, and dark flow becomes something extraordinary. Possible evidence that our universe is being tugged by structure in a larger multiverse. Other regions, other universes pulling on ours across the horizon. That is a staggering claim to hang on a temperature signal measured in millionths of a degree. And this is where the story turns from discovery to dispute, because a lot of cosmologists never believed the signal was real. The kinematic Sunyaev-Zel'dovich signal is one of the faintest things anyone tries to extract from the sky. Buried alongside it are the CMB's own natural fluctuations, instrument noise, and the light of the clusters themselves. Teasing out true motion is brutally hard. Critics argued the effect Kashlinsky's team found was so small it could be an artifact, a statistical fluke, or a subtle error in how the cluster signal was separated from the background. Then came the strongest challenge. In 2013 and 2014, the team behind the European Space Agency's Planck satellite, a far more sensitive successor to WMAP, ran their own search for the same kind of bulk flow. The Planck collaboration reported no significant dark flow. Their measurements were consistent with the standard picture. Any large-scale bulk motion was small, well below what Kashlinsky had claimed, and compatible with ordinary statistical noise. For many researchers, that settled it. Dark flow looked like a signal that vanished once you brought a better instrument to bear. The fate of many bold claims in cosmology. But Kashlinsky did not concede. His team argued Planck's method wasn't actually testing the same thing, that the way Planck handled the cluster signal effectively removed the very motion they were trying to detect. He and his collaborators published follow-up analyses using their own catalogs of clusters and continued to report a coherent flow in roughly the same direction and at roughly the same speed as before. So the dispute never cleanly resolved. It became a standoff between two teams reading the faintest of cosmic signals with different methods and reaching opposite conclusions about whether the flow exists at all. Underneath it lurks a hard limit called cosmic variance. We have only one universe to observe and only one sky. When a signal is this weak and this large scale, there may simply not be enough independent data to ever be certain. There's a separate, quieter puzzle feeding the debate. Even setting dark flow aside, several independent surveys have found that our local patch of the universe seems to move a bit faster and a bit farther than the simplest models comfortably allow. That's a much milder anomaly than a multiverse tugging on us. It might just mean there's more mass nearby than we've mapped, hidden behind the bright band of our own Milky Way. But it keeps the underlying question alive. To break the deadlock, cosmologists need what dark flow always lacked: more clusters, sharper maps, and a cleaner measurement of that Sunyaev-Zel'dovich fingerprint across the whole sky. That's coming. New ground-based observatories like the Simons Observatory in Chile and the planned CMB S4 project will map the microwave sky with far more precision and combine it with vastly larger cluster surveys from telescopes like Euclid and the Vera Rubin Observatory. With that data, the kinematic Sunyaev-Zel'dovich effect becomes a real precision tool instead of a marginal detection. If a genuine large-scale flow exists, these surveys should either confirm it firmly or rule it out for good. Step back, and dark flow is really a test of how well we understand the larger scales of reality. Standard cosmology insists motion should average out to nothing across billions of light years. Dark flow, if real, says something is quietly breaking that rule. Either outcome matters. A confirmed flow would be one of the first hints of anything beyond our observable horizon, a physical clue about a universe far larger than the part we can see. A clean null result tightens our confidence that the cosmos really is smooth on the grandest scales. For now, dark flow sits in that rare category of claims that are neither confirmed nor fully dead, proposed in 2008, challenged by Planck, defended by its discoverers, and still waiting on better data to decide. So here's the open question I'll leave you with. If galaxy clusters really are drifting towards something we can never see, what is doing the pulling? Hidden mass just past our horizon, or a scar left by inflation from before the Big Bang? Tell me which explanation you'd bet on down in the comments. And if you want to be here when the next generation of telescopes finally settles it, subscribe. There's a lot more cosmic mystery where this came from.